let's now move on to the next topic, namely uncertain choice. And before we get into the details, I'd just like to read you this quote here on risky decision making. For an organism, the biggest gambling game is investing its limited energetic resources into pursuing some prey or food source in the presence of uncertainty about the likely yields from such efforts. Consequently, there's biological survival value and thus selective pressure in being a good gambler in the real world, where too many bad gambles can result in the ultimate loss, namely death. So what this is basically telling us is that evolutionary pressures have already adapted our brain to dealing with uncertainties and trading off, costs with benefits in our decisions. So this is something that may not be clear to economists at first glance, but biologically we actually have to deal with scarcity. We have to deal with effort that we put into the outcomes. But we also have to accomplish those outcomes. We have to find food and shelter and be able to rest, to be able to survive for longer periods of time. So our brains, in a sense, are well adapted to risk and decisions involving risk and effort. But does this generalize to financial risk, such as in economic markets or when it comes to making decisions about financial outcomes? So this is a question that we'll answer here in this next video. It's important to note that there are different types of outcomes, namely known probabilities, which are referred to as risk by Knight in 1921, and unknown probabilities, which are referred to as ambiguity. So when we know probabilities, what this means is, for instance, in the case of a coin flip, where we know that if we have an even coin, that the chances of getting one versus the other outcome, so heads versus tails, is about 50-50. When it comes to unknown probabilities, situations where we don't know the outcome commonly occur in real life. Much of this is currently playing out with the current pandemic, where we're still learning about potential outcomes, for instance, related to how much vaccines protect you from getting a disease. But as we learn more about this, obviously, the probabilities will become better known. There are two additional sources of uncertainty that we need to distinguish between, namely unintentional uncertainty, which is basically based on a random number generator, such as a coin flip, or intentional or strategic uncertainty, which is based on the behavior of an opponent in a game that allows strategic behavior, basically, such as in a trust game or in an ultimatum game. Here in these next few studies, we'll focus on unintentional uncertainty, but we'll also talk about intentional uncertainty in the future. So let's consider one of these studies. You might remember this study from an earlier lecture or an earlier video. This is this famous study by Platin-Glimcher, published in Nature in 1999, in which monkeys were asked to perform a cute saccade task for rewards. So they had to shift their eyes to an instructed stimulus, and if they did well, then if they did this correctly, and it's not a difficult task, then they would receive some amount of reward. In this case, in one part of the study, they looked at how the neuronal responses in lateral interparietal area were related to the probability of receiving a reward. So one stimulus was associated with only a 20% probability of receiving a highly valued juice reward. Another stimulus was associated with an 80% probability of receiving the same reward. So depending on where the monkeys were instructed to look at, they knew already this is going to be a 20% or an 80% likelihood of a reward, of a highly valued outcome, basically. And we can see the neuronal responses in LIP here plotted for the different probabilities. In the black line, we see the 80% probability trials, and in the gray line, we see the 20% probability trials. And you can see that neurons in LIP fire more vigorously after the target onset, so when subjects were instructed to move their eyes. And you can see that this continues throughout different task phases. So in two task phases, you clearly see higher responsiveness in LIP neurons in response to 80% predictive cues relative than relative to 20% predictive cues. And here you see that this plays out over the different task phases. So this is one piece of evidence that the brain does respond to probabilities of outcomes, and in this case it does so in the neurons within LIP. Another another study shows this here, showing the responses of VTA and substantia nigra neurons, also in monkeys trained again on a instrumental task. So they got some conditioned stimulus, which is shown here with this bar, and then they had to perform some action for it to receive some reward, which is shown here in this bar. So at different time points in the task, they received different events, basically. One event was the conditioned stimulus, which is just let's say a light flash indicating the probability of reward, but you can change the type of stimulus and associate different stimuli with different probabilities of reward, as was done in this study. And then you record neurons within ventral tegmental area and substantia nigra. Those are dopaminergic neurons. And what you observe is the following. When the conditioned stimulus is highly unpredictive, then there's no responding to the conditioned stimulus. So the prediction, it's predicting a 0% probability of reward, but when the reward then occurs, there's a large response to the reward. So in this case, the monkey thought there was not going to be a reward, and then there was a reward. So this is basically like a prediction error, right? Like a positive prediction error. We can see that the same similar events happen, but that the distribution between responding to the conditioned stimulus and to the unconditioned stimulus changes a little bit. So when the probability is 25%, the predictive probability of the conditioned stimulus, then you see a somewhat larger response to the conditioned stimulus and still a large response to the unconditioned stimulus, so the reward stimulus for the monkey. Then this increases here to 50%, 75%, and 100% in the end. And again, what you see is increasing responsiveness to the conditioned stimulus and decreasing responsiveness of these dopaminergic neurons to the unconditioned stimulus. And as a side note, each of these dots here, just to interpret these figures, each of these dots represents one action potential fired in VTA and substantia nigra neurons. Going down the line means these are different recordings from different neurons. So every line in here reflects or represents a different neuron. And then these plots here are the average responses of these neurons. We can also replot this as the average response of these neurons, which is here the median response of these neurons, normalized, versus the probability of reward across 3 different animals. And you can see that the average response of these neurons increases to the conditioned stimulus as the reward probability of that conditioned stimulus increases. Test. Good. We can also do these types of studies in experiments in the fMRI scanner, obviously with humans. And what's done there typically is we offer participants a chance between different types of gambles. So here's one example of this type of gamble that's commonly given to participants inside the scanner. And you can see that here's a choice between some chance of getting 50 euros versus a larger chance of getting 12.5 euros, and a similar gamble that offers 25% 25 euros and 15 euros at equal probability. You can see also here that in this example that I'm giving here, the expected value of the left and the right lottery are exactly the same, right? So this is a 20% chance here and an 80% chance here versus 50-50. So what we do in these experiments typically is vary the amounts and the probabilities offered on each trial And then this is the kind of experiment that you do to investigate basically risk-taking and the neural correlates of risk-taking in the fMRI scanner. In fact, there are a number of studies that have conducted these types of experiments, and they have found a different set of regions involved in these types of tasks. So when it comes to risk, we find commonly the anterior insula involved in this, but obviously also regions adjacent to this. So that's what's shown in these red regions here. These regions typically show an increased responsiveness to increases in risk. So the worse something gets, the higher the activity in these regions, which is sort of giving a warning signal or a neural correlate of a warning signal in the brain. And that's what the anterior insula might be doing here. We also have regions, obviously, that are involved in these types of tasks because making decisions over risky choice options also involves making decisions over expected rewards. So the ventral striatum is commonly involved in this, and other regions that are involved in inhibitory processes, such as the dorsolateral prefrontal cortex, and also involved in executive control, such as the posterior parietal cortex. So this is based on a meta-analysis by Platt and Hutel, showing the involvement of different types of regions in different types of, moments, if you will, statistical moments involved in processing risky choices. But let's have a look at this study that makes a distinction by Preuchow et al. In 2006 that clearly distinguishes between the role of the insula, which is clearly involved in risk, and the role of the ventral striatum. And they use this wonderful task that is quite intuitive to participants, but allows the researchers to look at how probability evolves and how probability and expected reward estimates evolve in this task. So at the beginning, participants have to make a decision about whether they want to bet on whether the second card is higher or the second card is lower. And at this point, the probability of the reward is basically 0.5. They don't know how this is going to play out. They haven't seen any cards. As soon as the first card is shown, let's say we betted the second card is going to be higher, we know what the probability of winning is. The probability of getting a higher card is actually 1/9 because there's only one card that is larger than the card that was already picked. So we know that we have quite a large probability of losing and quite a small probability of winning. So we would be somewhere down here. Probability of reward is 1/9, right? So our risk is relatively low because we can estimate exactly what will happen on the second draw. Or not exactly, but what will likely happen on the second draw. Our expected reward is also low. But then as we move along this continuum, you can see that the probability of reward at 0.5 leads to maximal risk, which is basically because it's the most unpredictable point in this graph. So at 0.5 probability, where everything is 50-50, you cannot predict whether you're going to win or lose. However, at 0.1, let's say, probability of winning, you can basically say with almost certainty that you're going to lose, and at 0.9 that you're going to win. So the risk in those two cases are exactly the same, but the expected reward will vary. The expected reward varies along with the probability of reward because the bet was always $1 per each trial, indicating that the magnitude was always the same, and the probability of reward would then be the only factor influencing the expected reward here. So this is exactly what we see here. As the probability of reward increases, the expected reward increases linearly, therefore. So we have these two components. The risk component, which is obviously measured here as the variance of the reward, or the squared probability of the reward, is nonlinear, or it's this quadratic function basically, whereas the expected reward is linear. And so this is something that we can therefore dissociate in the brain when we look at the neural correlates of both risk and expected reward. So in the brain, we can see that there's a linear match between the probability of reward and the neural responses when the first card is shown. So this is indicating that the striatal region here is involved in computing basically the expected reward. And that's what we've seen before. So reward is represented here, but this might be a function of the expected value or the subjective value of the outcome, as we have seen in many other studies before. So we have the left striatum here and the right striatum here showing these linear increases as a function of the probability of reward when the reward is constant, and therefore the probability of reward here increases the expected value of the lottery or of the game. On the other hand, we have this nonlinear or this quadratic response that's reflected in the left and the right insula. And this is really showing that the insula is involved in estimating the risk or the variance of the reward in this current study. So we find a dissociation between the insula and the striatum here, where the striatum seems to be encoding more a linear function of reward, which is reflective of the expected value of reward, whereas the insula bilaterally seems to encode the variance of the reward, which is a reflection of the risk involved. The finding that the insula is involved in risk or in estimating risk of your environment or of stimuli that you're choosing over, so of outcomes of your decisions, is consistent and has been replicated now a number of times. It's also consistent with other findings that implicate the insula in identifying basically negative stimuli in your environment. And risk is one form of this, right? It's estimating the negative side of certain outcomes in a sense. So to show some of these similar findings from this review by Singer et al. Here, the activity correlates with electrodermal arousal. That is basically the amount of sweating, which is a proxy of your autonomic nervous system activity. You can be aroused in the positive domain, but many studies also measure arousal to negative stimuli. So for instance, when you're stressed or anxious, then this activity will ramp up. It's also correlated with or enhanced when you empathize with others that are in pain. So empathy leads to increased activity here. And one reason here could be that this is estimating the probability of a negative or an aversive event occurring to you, because you can see it occurring to another person. The estimate then would be what's the likelihood of it occurring for me. But it's commonly also used as a measure of empathy. Additionally, it correlates with interoceptive awareness, as shown here, and that is how well you can monitor your physiological states. Also, the same authors, so Preuschow and colleagues, have shown that the insula is involved in risk prediction errors and risk prediction, as shown here by the blue and the red neurocorrelates. So both of them are encoded in the insula, but are also spatially separated in a sense. So this all indicates to us that the insula seems to signal to us when something aversive is happening to us and how aversive this event is. So it ramps up signal amplitude the more aversive something is, and the riskier something is, in a sense. While this all makes a lot of sense, as a side warning, we don't want to engage in reverse inference here. The insula is also involved in many other things, and therefore we should be careful making these kinds of conclusions, but it is consistent, and this consistency should be noted here. So let's have a look at this interesting paper here by Ming Su et al. That was published in Science in 2005. And what they did is they had 3 tasks: a card deck task, a knowledge task, and an informed opponent task. So there was a social component here as well. In the card deck task, participants were basically making a bet on one of these 2 cards. And if a blue card, let's say we bet on a blue card, and a blue card is drawn, then we receive $10. If a red card is drawn, then we don't receive $10. Or they take a $3 payout for sure. This is the risky condition where we know exactly the distribution, so we have a 50-50 chance to, get either a red or a blue card that was drawn. So a bet has a 50-50 chance of yielding $10. In the ambiguous situation, however, We don't know the distribution of cards. So we don't know how many red cards on each trial there are, and we don't know how many blue cards. So betting here is ambiguous. There are 20 cards in total, but the distribution could be, let's say, 17 red cards and only 3 blue cards, and we don't know this distribution. So this is an ambiguous situation where the exact distribution, the exact probabilities are hidden to the subject. Similarly, in the knowledge task, we have a risk task about where we're guessing the temperature in New York City on November 7th and whether this is above 50 Fahrenheit or not. And then the answer is simply a yes or no. And if it's correct, then this task yields $10, or the participant can just opt out and go with the $3 option. In the ambiguous task, a similar question is asked, but it's about a city, Dushanbe in Tajikistan, on the same time, so November 7, 2003, and with the same units basically, but we don't know as much. So these were US participants, and participants didn't know as much about this particular place, where it is located on the globe, and this lack of experience makes this an ambiguous situation relative to New York City, which there's a lot more knowledge about this and can be guessed much more easily. And finally, there was an informed opponent task where the participant bet on a task, an opponent then bet on the opposite task, card. So the opponent bets on, let's say, the blue card, then you have to bet on the red card. But in one case, your opponent is uninformed. He did not, or she did not, draw any cards from this deck. That is ambiguous again here, right? So it's more about betting against another opponent, versus in the informed opponent condition, where the opponent actually drew 3 cards and then makes a bet. So the opponent got to sample a subpart of the distribution of the cards and therefore is better informed. And this makes this a much more ambiguous situation than this situation here, because the opponent will likely bet on the more common color, and that is a reflection of the distribution of these cards. So what the researchers then did is they looked at all the ambiguous decisions that participants made and compared them to the risky decisions that participants made. And this allows them to identify regions in the brain that are activated more during risk relative to ambiguity, and vice versa. So let's have a look at the risk regions. And there's no surprise here. This is the striatum that has been implicated before in risk in the Preuchow study. And we see that the striatum shows an increase during risk trial in activation relative to ambiguity trials. You can see this in both striatums, both the left and the right striatum, so in both hemisphere. And then there's a bit of a dissociation between the tasks, but we're not so interested in this. So what the researchers argue here is that the striatum is involved in risk, but not in ambiguity. Now, a similar thing can be done when it comes to ambiguity. And here we find that ambiguity is shown in blue and risk is shown in green again, that the amygdala, again bilaterally, and the lateral orbitofrontal cortex, also bilaterally, seem to encode the ambiguity involved in a decision that participants are making. And both of these regions, the amygdala and the OFC, show an enhanced activity during ambiguous trials relative to risk trials, implicating these two types of regions in ambiguity rather than risk. So the initial paper by Ming Su was then followed up by this really interesting paper here by Ifat Levi, published in 2010, and they used a somewhat different task that allowed for varying the amount of ambiguity on each trial. So this is an urn that was shown to participants here with a number of balls basically in one versus the other condition. So there are more blue balls than red balls here. In a sense, it's a sort of reflection of an urn, right? So we have actual probabilities of having the blue outcome versus the actual probabilities of having a red outcome. It could also be seen as another way of showing a pie chart in a sense. But then there was also a value associated with each of these outcomes. So a blue outcome and a red outcome and also the probability was clearly seen in the risky trials. That varied between about, I think, 13% in one condition up until 80% in another condition. So it varied across a range of different values, as is shown here in these figures. So this is a high likelihood of getting a blue outcome. This is an even higher likelihood of getting a blue outcome, and a very low likelihood of getting a red outcome, and the opposite is shown here. And again, this was then associated with different values for each of the different outcomes. Now, given that there were many trials involved in this, the experimenters were then able to get a subjective value from this lottery, which is basically measured as the probability offered on a given trial. So in the risky trials, in the ambiguous trials, this was set to 0.5. And then the ambiguity, which varied across the ambiguous urns, was also associated with a parameter, namely this beta parameter here, which is a reflection of the ambiguity aversion. And then obviously the value of the lottery, which was modeled as a power function, just like it is in prospect theory. So the important thing here to note is that the authors introduced these ambiguous urns, where ambiguity could vary between 25% up to, I believe this is about 75% here, and 50% here. So this is modeled via this A parameter in the subjective value term. And across different trials, they were therefore able to identify this ambiguity parameter that basically allows them to estimate the subjective value, not just on risky trials, but also on ambiguous trials. So this is an interesting task that allows for this, inspecting the subjective value correlates while participants are making either risky or ambiguous decisions. So let's have a look at the neural correlates of this. So when participants are making risky decisions, and we have seen this network before, we see activations in ventral striatum, ventral medial prefrontal cortex, but also in the amygdala. And that had been shown previously also. So the amygdala was associated with, I believe, ambiguity in the Ming Su paper. We see a similar network active when we look for the neural correlates of subjective value in the ambiguity trials. We see again ventral medial prefrontal cortex, but also striatum to some degree, and also amygdala. So the amygdala activation here is in a sense replicating the Ming Su paper findings, but we also see this in the case of risk. Note that we're looking at subjective value correlates here. So that is the correlation between the subjective value on a given trial that was extracted from this equation here and changed on a trial-by-trial basis, basically by varying the risk level of each urn and the ambiguity level of each urn, and then the outcomes associated with each urn. And we find similar networks involved both in decisions under ambiguity and under risk. There was one additional finding, however, involving the lateral orbital frontal cortex, and that region seemed to exclusively encode the ambiguity level involved in a given decision, because it showed, if you look at just the blue lines, which are reflective of the ambiguity levels, it showed a ramping up of the activation as a function of ambiguity level, but not as a function of probability. And this is actually basically replicates the findings by Su et al. Again, showing that this region, the lateral orbital frontal cortex, is involved in processing ambiguous decisions.